So, in this lecture we discussed in detail about the principles of ultimate load design. There are different limit states for which design is being deployed in marine structures, but these limit states are not only common or not only specific for marine structures, very common state, but let us discuss them in detail as applicable to marine structures in couple of lectures from now. Now the most important question asked is, what is the fundamental objective of any design? We have to start from this origin, then only we will understand why we bother about ultimate load design. So what is the fundamental aim of any structural design? I am focusing only on structural design. Why it is so? The answer to this question is, the structure chosen for a specific purpose very carefully understand, structure is chosen, it is not designed, you are choosing a structure. This statement is very much valid for offshore structures because offshore structures generally not designed, they are chosen from the time tested geometry available in different sea conditions or sea states. We only modify the characteristic of the objective of the geometry, do experimental investigations, try to invest them on real sea states. So structure chosen for a specific purpose, as I said, FSRUs, FPSOs, FSOs, etc., specific purpose, should sustain the loads and deformations, both are important. Load is an external agency, deformation is an internal reaction, both should be within the limits, should sustain the loads and deformation resulting within the lifetime. Now it is a very general statement, no, because you say the structure should be chosen accordingly to deliver a specific function or a purpose and should sustain loads and deformation. Now every principle of structural design is having this. What is special about marine structures? With margin of safety, this is very important, because our installations and marine structures are very expensive, okay. We cannot afford to lose the system because commissioning, installation, planning, design, member accumulations, etc., are all very expensive and it is a very long term process. For installing one platform, for commissioning a platform, for a production of let us say oil in deep water takes minimum about 6 to 8 years, and this will affect directly the economical criteria of any country. So you cannot take a chance of losing or doing wrong calculations or let us say accepting by default certain values and going out of the structure. One. The second important aspect is why safety is important, because not that 50 people are on board, it is not that. If that is the case, then schools, hospitals, libraries, etc., should have higher margin of safety because more people live there. Theatres, shopping complex should have more because more volume of people are there. It is not the focus of people who are on board. To say very sorry, it is a very important fact that equipments are very expensive for me. All my equipments are specially designed, okay. I do not want to lose even 1 inch of any of the functional part of the equipment for any reason being there. Third, these structures are always located in what we call as an hostile environment. You do not have an access to them, you do not know actually how are they behaving. you are not monitoring them continuously, you are staying somewhere on shore, you really do not know. Okay. So, there should be an inherent system of safety inbuilt in the design itself, so that the structure does not fail from its intended function and remain safe. Third reason. The fourth reason is the environmental forces which this structure is encountering is highly unpredictable. Though we have seen list of forces, though we have seen spectrums, equations, mechanical methods, analytical studies, experimental verifications, literature, codal recommendations, all will land up in lot of uncertainties. This level of uncertainty as applied to marine structure is unique in the structural engineering domain itself. There is no other structure on earth which has this kind of uncertainty like a marine structure. So, we have to insist on a very important aspect that my design principle should lead to a safe output of my choice of the structure. Remember, design is a choice. What does it mean? I cannot make a given structure to be safe against these. I have got to select a structure to remain safe against this. You remember there is a difference, exactly this is where we deviate from a conventional structure to a marine structure, because we do not do the design from form, we do the design from function. I want an oil exploration at deep water, the depth of water is 2500 meters, it is hostile environment, wave heights and wave periods are very high, earthquake loads are sensitive, wind load is very high, maybe 30-40 knots. So, I have seen all these characteristics and choose a form which does either drilling, only production, production and storage, only offloading. I have got different functions, you understand. So, I have to choose a form which will be safe. This is where we fundamentally deviate from a classical structural design of any other structural systems, and above all we deviate because our structural systems are unique, because the numbers of marine structures constructed in the world so far maybe will not exceed even 600-700, whereas in IIT campus itself you have got about 1000 buildings. So, the number, the investment in terms of numbers of structure, money, direct link of these kind of structures on economical consideration of the country are all very highly important in nature. Therefore, we have got to be very careful. So, safety is not meant for saving human being, please understand this. I have got only 50 people on board, I am not bothered if all the 50 dies, I am very sorry to say this, but that is the fact. We have more investment towards process equipments, we have more investment and interest towards the functionality of the platform, and lastly, if the structure fails, it will have severe consequences of marine pollution, okay, oil discharge in sea, marine aquaculture being killed or made extinct, and decommissioning causes lot of difficulties in terms of financial implications to the owner of the structure, or to the country where it is installed, or to the sea where it is being floated. So, we cannot take a chance. Okay. So, for example, if a land based structure, if it is destroyed by a natural calamity like an earthquake or a wind effect, the failure or the consequence is local, whereas if a marine structure fails, the consequence is immediately global. So, the factor of safety or the margin of safety should be very high for these kind of structures. Okay. Now, the question comes, since the margin of safety is required to be high, structural design is essentially finding the member dimensions. If I get a member dimension as 1 meter diameter, can I go for 3 meter diameter, make it very strong, very safe, because margin of safety is very high. Remember, very important, the moment you keep on increasing the diameter, your weight is increasing. The moment weight is increasing, you are paying for it in terms of commissioning, installation, material, cost, investment, decommissioning, everything, and seismic. So, you cannot afford to have a enormous abnormal size of members as well. So, we have got to intelligently play a balance between the form arrived at and the sensitivity of the structure. So, specific objective of any structural design in general is to make the structure safe, to perform or to intend to perform the specified function or to deliver decipher loads and deformations within its service period. Now interestingly, I have a lifetime of a platform 10 years. I will come to the examples later, mathematically I will show you 10 years. I have designed the system for 10 years, but after 10th year I am not interested to decommission the system because the system is producing oil. I do not want to take it out. Any 1 year of extension without redesigning the structure, without strengthening the structure is a questionable thing. Safety will be compromised. Okay. This is true in land based buildings also. For example, building life is about let us say 50-75 years. You have got heritage buildings which is about 300 years. These buildings must have been demolished, but people make them as monuments and people visit in by and large. VIPs also go there, is it not? But the structures are not modified, they are not even strengthened. People want to maintain the original architecture as it is. Okay? Why these things are done? Because they are preserved as a monument. But here that importance is not given to the structures because functional platforms, no platform is a monument, it is a functional platform. Okay? Therefore, it is very important that the service life or the lifetime, within the lifetime we guarantee, beyond the lifetime we do not guarantee. What is that consequence? How do you handle this in design? If I say I am going to exceed the service life, I must understand mathematically what will happen to my structure. I must understand this mathematically first. All these mechanisms should be brought explicitly in the design, which is called ultimate load design. Okay, this is one of the limit states. There are 4 limit states by which marine structures are designed. Let us now say, let us say limit states of design for, I should say, marine structures. First let us understand what do you mean by limit state. The performance and function requirements of marine structures. I am using MS for marine structures, I think that is easy for me to, you can abbreviate it, or generally explained in terms of limit states. So these are the limits, up to which it is declared safe. If the limit is exceeded, it is dangerous. So one may wonder physically as an engineer to ask a question, sir, we are allowing a structure to go to a limit, maybe an upper limit. Limits are there both, lower limit, upper limit. Let us take about an hypothetical case where I am designing a structure to an upper limit, take it to the maximum limit, and we understand if it exceeds that limit there is a danger. Now we do not have a control on the loads because they can exceed, we do not have a control on the service period, they can be extended, we do not have control on material deterioration because of corrosion happening in the sea environment, we do not have control on operational speed and operational pattern of the equipments on top side of the decks because they are all depending upon how much oil is being produced. When we have no control on any of these aspects, how can you design a system which is having a limit state? It is dangerous mechanism as such. The design itself is a wrong phenomenon because this will lead to danger. Moment it is exceeded, failure is guaranteed, whereas I want safety. Why are we suggesting this? Fundamentally, why do we suggest this design methodology for marine structures? We will answer this after a couple of lectures. It is a very critical, serious question which one must ask. To answer this question, first let us understand thoroughly how limit states are examined and employed for design. Once we understand this question can be comfortably answered with a good meaning, but this question is a very critical question, you must understand, because this is it foregoing safety, is there any compromise on safety in this kind of designs, we must understand. If there is no compromise, then it is acceptable. Okay, we will see this. The first is ultimate limit state, the second is fatigue limit state, I will expand this. The third is progressive failure limit state, the fourth is serviceability limit states. So, this is ultimate limit state, this corresponds to maximum load carrying capacity. I am underlining here, this design mechanism tells you what is the maximum load the system can carry, give you a warning. So, it is talking about upper limit, maximum limit. Okay. This is fatigue limit state, this corresponds to damage caused by repetitive loading. So, here the magnitude of the load is not important, it is the number of cycles the load is being repeated is important. In the first case, it is the magnitude which is important, is that clear? Because we are talking about maximum, we are talking about the magnitude, amplitude, but here we do not talk about the amplitude, we talk about the number of cycles. So, low amplitude large cycles, high amplitude short cycles, can be any combination, we talk about number of cycles here, that is what we call as repetitive loading, that is called fatigue limit state. The third one is progressive limit state, we call this as limit state of progressive collapse. This corresponds to progressive collapse caused after a damage is initiated, that is very very important. Or rupture occurred. What does it mean? You already have a system, a member, the member has already failed, okay, the member has already failed. After the damage has occurred in the member, then the failure will, the collapse will start, that is called progressive collapse, okay, non recoverable. Then this is serviceability limit state, serviceability limit state. This corresponds to normal use and durability. This corresponds to normal use. When the structure is subjected to a conventional use and durability, you talk about limit states, that is called serviceability limit state. There are 4 limit states which are advised for marine structures by international courts, out of which we will speak about one only in this module, in this lecture. We will also talk about fatigue design later, we will not talk about progressive limit class, we will talk about slightly this in the plastic design, just a hint, and so on. Now let us quickly see what do they include. If you talk about ULS, it includes the collapse modes of the structure. You may wonder, when there is a special limit class available to talk about progressive collapse, why ULS will talk about collapse? Very interesting, very fundamental question asked. Look at the stress strain curve of any material, let us say steel. Why steel? Steel is a common material which is being used widely in marine structures. Okay. If we say stress and strain, that is a classical stress strain curve I have for a stress strain curve I have for a mild steel. Of course, the modification occurs on this stress strain curve depending upon what material you are adding to it for improving its durability, ductility, weldability. We will talk about all those things in this next lecture. This gets modified. Now we all understand that my yield value lies here, up to which the material remains elastic. My ultimate value lies here, up to which the material is safe, beyond which it is failing. It means very clearly we said that from the yield to ultimate there is a non-linear phenomena happening, which is post elastic behavior. Okay. What do you mean by post elastic, or what do you mean by non elastic? Non elastic refers to, in simple terms, of leaving permanent deformation. Permanent deformation can be a crack developed. So at this stage it is going to collapse. So when we talk about ultimate load, I must talk about collapse. Then what is the difference between talking collapse with ultimate limit state and discussing collapse in PLS? This collapse is progressive, which happens after a damage is initiated, already damage is created. Then the collapse becomes progressive. Now you may want to ask me a question, sir, here also after an elastic stage damage has been initiated, but this is a material damage, this is a structural damage. Just because one of your fingers failed, you will not be declared dead. People live, physically handicapped, people live, is it not? This is a finger loss, this is heartbeat loss, but still people live, even the heartbeat, or even when you got a collapse, that is called coma stage, it is progressive collapse. Okay. Maybe your grandma fell down, she had a head injury, admitted in the hospital, damage is initiated, she is kept in ICU for 6 days, progressive collapse, ultimately 6th day she died because of heart failure. That is a stage of collapse completely, that is a progressive stage. The grandma lost or had a hit in a head or a brain is material failure, then she collapsed because she reached an ultimate stage. Okay, there is a difference. So in ultimate limit state we should talk about collapse. Then one may say, sir, where are we talking about collapse of material? I talk about collapse modes of structure. Every mode is associated with a damage in a material or in a member. So collapse modes will be discussed in ULS. The moment I say collapse modes, let us give some examples. One talks about excessive yielding, which transforms the structure into a mechanism. I will talk about this particular phrase mechanism later in plastic design. What do you understand by a mechanism? We will talk about this. It also addresses buckling due to elastic or elastoplastic instability. So, this will lead to loss of equilibrium in part or to the whole structure. Okay. Can be either local, can be global. So, these two aspects must be addressed in ULS. For completion sake, we will also see what are addressed in FLS, PLS and SLS also. Okay. FLS is important and includes the stress concentration which occurs due to reversal nature of the forces. That is what we call a cyclic loading. People sometimes call this repetitive loading, sometimes people directly call this fatigue loads, arise generally from waves, wind, current, live loads, machineries, etc., which are all very much present in a marine structural system. Talk about PLS, progressive limit state. This will include failure caused by accident loads. Serviceability limit state. This is linked or includes the general serviceability requirements governing deflection and vibrations. I can give an example. Let us say we can give an example for SLS, because then one will not be able to appreciate what are we discussing in LS, SLS and what we will discuss in ULS. Of course, one is very clear, I hope, between FLS and PLS there is a difference. You talk about here repetitive loads, though wave load is also a part of ULS, but here we are talking about repetition of the cyclic of these loads coming on the member, which imposes stress concentration. This does not happen on all the members, it happens only at specific points which are called as hotspots in a given member, okay, or a system. So only those will be examined critically for FLS. And of course PLS talks about accident loads. Let us imagine hypothetically no accidents do occur or expected to occur in marine structures. Let us say we does not focus or we do not focus on PLS. Now in SLS we include general serviceability, whereas in ULS we talk about ultimate load carrying capacity. Can this be combined? Can I combine both SLS and ULS and call this as one single limit state? The answer is no, it is not possible, because one talks about acceptable serviceability requirements, one talks about the maximum load carrying capacity. There are two things. I can give a physical example. Let us say we have a porter, the person who intends to carry luggage, okay. Now the acceptable capacity of a porter, let us say for example, is approximately, I am saying 50 kg, he is a well built porter, 50 kg. Per kg it is 2 rupees as per the Indian Railway Regulatory Boards, etc. So you have to pay him 100 rupees if he carries 50 kg. Now you have got 120 kg weight, you need only one porter to carry, because if you have got two, you have got to run behind both of them, which is not possible. And he will not bring the second one because he does not want to share his income with the second one. So we are now talking about what is the maximum load he can carry. This is ultimate. The moment he is intending to carry the ultimate load, he is already undergoing certain damage. The damage can be either to himself or to your material also. He may drop your luggage, etc., may break, okay, that risk you are taking by hiring him. The moment you say ultimate load design is done, you are imposing, you are accepting certain level of damage to happen. If the damage should not happen and should remain within acceptable level, it is SLS. So in SLS we talk about acceptable serviceability. It means my platform should not sway or surge beyond, let us say, 3 meters. Whatever may be the load, whatever may be the condition, whatever may be the reversal of loads, wherever the platform is installed, sea state, nothing, I will not allow the platform to go beyond 3 meters. It is not because I stay on the platform, it is because if my platform moves beyond 3 meters, the flexible connections between the drilling derricks and my drilling strings will get damaged. So there is an operational restriction. So I say that is my acceptable serviceability in terms of deflection. In terms of vibration, the platform deck vibration should not cross 0.05 G, that is 0.05 of 9.81 maybe, etc., xy value. Why? Because this will cause lot of secondary mass activity on my machinery. I keep a machine on a table which is static, operate the machine, performance of the machine is x in terms of its efficiency. I put the machine on a vibrating platform, vibrate the platform horizontally and vertically, very high value, and operate the machinery, performance is y, efficiency. You will see efficiency y will be much lower than x. So I do not allow that vibration to happen in my platform deck, at least in heave direction or in yaw direction, whatever may be the degree of freedom we are discussing. So we fix up certain acceptable levels which we call them as serviceability requirements. If you focus the limit state based on that, that is called serviceability limit state. Do not bother about serviceability, look only at the maximum load carrying capacity, then talk about ULS. You understand? Now the question again, the second critical question comes. First question I have already asked. The second question comes is, in ULS are we compromising serviceability? Are we compromising serviceability? If that is the case, then ULS should not exist at all, because I do not want serviceability to be compromised. If it is yes, If it is yes, it is not compromised, then what is the difference between ULS and SLS? Okay, there is a roundabout question here. The second critical question which you must understand when we discuss about all limit states. Now, are you able to distinctly understand the difference between the limit states or not? We have got 4 limit states, 4 of them are distinctly different, there is no overlap except marginally, but by and large they are different, they are not same. Okay. Now, there is a counter question coming between SLS and ULS, etc., as we just now posed a question to you. So, how this is answered? Does ULS compromise on serviceability? If yes, then I do not want ULS. If ULS is adopting serviceability, then why 2 limit states? The answer is very simple. I design for ULS, check for serviceability. Now, the question is acceptable standards. I design for ULS, check for serviceability, the serviceability accepted by you is 3 meter, I am getting 3.5, I make that as acceptable to you. Why? Because the advantage derived is ULS is an economical way of design. Okay. So, you redefine the acceptable standards based on ULS. So, of course, remember, for the platform to remain functional, both should be satisfied, there is no compromise on either one of them. Okay. But you may not go for a ULS, I do not want to go for ultimate load design, I do only elastic design, people have been doing it, but there has been no design existing on earth which has compromised SLS. Serviceability is a mandate, you must meet the requirements. ULS is an added advantage on the system design. Is it clear? So, this is must, you have got to meet this requirement, but in ULS we slightly modify this, we are not ignoring it, we are not compromising it, we are modifying it certainly, we check it. Is it clear? So, this is a new design process, it is a checking process. So, serviceability are generally assessed, ULS are generally designed. Is that clear? You design for ultimate state, limit state, check for serviceability. So, you do not design for serviceability and check for limit state, ultimate limit state, we do not do that, it is not a reverse process. Is that clear? That is why we say ULS is a design methodology. Okay, we check this, I mean we design this, of course we assess it here. Now, the question comes when we talk about assessing the reliability of any structure, whether the structure is safe, will I check the serviceability or load carrying capacity? When will I say the structure is not reliable? Is it the load carrying capacity is exceeded or serviceability is exceeded? It is a very interesting question, it is a third critical question again, because there are 2 different limit states. Is that clear? The fourth question, of course, is very obvious, you will be able to answer if you are a structural engineer. Why elastic design is inferior to ultimate load design? Why elastic design is inferior? I am giving a hint, it is inferior. Why? To ultimate load design.
All the layers don't take the strain
Equally.
So, till the last layer in the section takes the strain, then the whole structure is economical.
So, what we try to say is very clear that in elastic design we only talk about the maximum strain in the extreme fibers, maybe compression, maybe tension. Once the maximum strain is reached in extreme fibers, we stop the design level there and based upon that strain, since it is elastic and is linear, stress is proportional to strain. From the strain, using Young's modulus, I get the stress, and for the stress I design the structure. That is elastic design. We are bothered only about the extreme fiber, okay. But in this case we talk about the whole section, so it is economical. therefore this is superior. Why? We are utilizing the section to its utmost capacity, beyond which section will not exist, it will collapse. Isn't it dangerous? We are exploiting the section, we are exploiting the section. Isn't it dangerous phenomena? If it is dangerous, then this design should have not been taught at all, okay, should have not been emerged at all, should have been stopped at that level itself. It is a question number 1 which we asked in the beginning, same question I am repeating again. By understanding a clear definition that in this design pattern whole section is completely and fully stressed or strained to the ultimate value, is indeed dangerous. Same question I am asking, okay. So this is superior obviously to elastic design, because full section is utilized. After all, I am paying money to form a section, I must utilize the full capacity of the section. I get a bicycle, I must ride it, I keep on need not have to keep on washing it and fill up the air and keep on watching it, I am not using it at all, is it not? So I must ride it, okay. I have a pen, I should write to the core until the last bit of the ink is present in the pen, is it not? So full utilization is a general psychology. So I have a member, I want to utilize it fully, so ULS, but isn't it dangerous? Because this fails when it is exceeded even by chance, okay. We have to answer this question, it is a very critical question, we have to answer this, okay. Not directly but indirectly by understanding the design principles. Remember, we will not do any design examples in this class of ultimate load design, that is not the class, it is the course on design is separate. We are talking about advancements in marine structures, we are talking about different design patterns. We will not solve any examples of showing how to do a limit state design or ultimate load design for a member on a marine structure. I think you have to look for a different course for that, okay. There are different courses available, you should look for different books. We are talking about fundamental phenomena, you are clear? Once the phenomena is clear, you can design, but without understanding the phenomena, if you design, still also you can design, but that will be only mechanical, you will not know why it is so, how it is so, etc. So our focus in this course is to explain you that phenomena with of course simple examples, but you do not please expect me to do a simple problem where I will do the whole design of ultimate load design for a member using international codes or any specific codes. We will of course refer certain classes, we will do certain numerical examples, there is no doubt, but we will be always speaking about the phenomena, the fundamentals, which is generally not understood when people do such design in some other courses. That is a general statement, I am not criticizing or commenting on anybody's this thing, it is a general statement. People have done designs using software without understanding the advantage, the differences fundamentally, okay. We will speak about that, okay. So we will stop here for this, continue in the next class.